We start the discussion on electrostatic forces acting on electric charge in dielectrics with the simplest case. When we studied electric fields in insulating materials, we considered the problem of a charged conducting sphere of radius R surrounded by a homogeneous dielectric medium of relative permittivity εr. We saw that the electric field E due to the electric charge Q distributed over the conducting sphere is spherically symmetric outside its surface, and its magnitude is εr times less than the magnitude of the electric field produced by the same charge distribution in a vacuum. The symmetry of the problem does not change if the radius R of the charged sphere tends to 0, and we obtain a point charge Q1 surrounded by the same medium. Hence, in an infinitely extended homogeneous dielectric medium of relative permittivity εr, the electromagnetic field E of the point charge Q1 has a radial symmetry about the point charge, and its magnitude at any point P is given by 1/4 pi times the vacuum permittivity ε0 times the relative permittivity εr, times the charge Q1 over the square of the distance r of the point P from the point charge Q1. As the form of the equation shows, it still holds that the magnitude of the electric field E in the dielectric is εr times less than the magnitude of the spherically symmetric electric field E0 produced by the same point charge Q1 in a vacuum. Now we can state that the magnitude of the force F acting between the point charges Q1 and Q2 surrounded by an infinitely extended homogeneous dielectric medium, is equal to the product of the charge Q2 and the magnitude of the field strength E due to the point charge Q1 that is evaluated at the position of the point charge Q2. Then we have 1/4 pi times the vacuum permittivity ε0 times the relative permittivity εr, times the product of the charge Q1 and the charge Q2 over the square of the distance r between the 2 point charges. This formula expressing Coulomb's law for dielectrics is only valid for liquid dielectrics. If the point charges are surrounded by a solid dielectric medium, then the problem of calculating the interaction forces is usually an extremely complicated task due to the various pressures and voltages that occur in such a situation. In the next example, let us consider an experiment where a metal sphere and a pith ball are suspended close to each other. The metal sphere is suspended through a metal wire which allows us to bring electric charge to the sphere, whereas the pith ball is hung by an insulating string such as silk or nylon. If we bring some electric charge Q to the metal sphere, then the lighter pith ball will move towards the metal sphere, which indicates that the two suspended bodies attract each other. However, if we repeat the experiment with the metal sphere and the pith ball immersed in turpentine, then we will find that the pith ball moves away from the charged metal sphere, indicating that there is a repulsive electrostatic force between the two bodies. This phenomenon can be interpreted by a greater degree of polarization in a substance with a greater dielectric constant. In the figure ε1 denotes the absolute dielectric constant of the medium surrounding the bodies, and the absolute dielectric constant of the pith ball is denoted by ε2. If ε1 is less than ε2, the excess charge built up on the boundary surface of the pith ball closer to the charged metal sphere is negative. If ε1 is greater than ε2, this excess charge is positive. In the first case, the positively charged metal sphere attract the pith ball, whereas the charged body will repel the pith ball in the second case. By comparing the electrostatic forces at the boundary surface of the pith ball closer and farther from the charged metal sphere, we can see that they act in opposite directions, but the forces at the side closer to the sphere have greater magnitudes. As a result, the net force acting between the two bodies is attractive in the first case, that is when the absolute dielectric constant of the medium is smaller than the one of the pith ball, and repulsive in the second case where the pith ball has a greater permittivity. The electrically insulating pith ball behaves like a dipole in the electric field produced by the charged metal sphere. Now we will give a quantitative description of the result of this experiment in several consecutive steps. First, we note that if a homogeneous charged body is placed into the non-uniform electric field E in a vacuum and the body is assumed to be small enough that the electric field is uniform inside the body, then the force F acting on the charged body is given by the charge Q of the body times the electric field strength E at the position of the body. In order to introduce a body with the charge Q into an electric field E in a dielectric medium, we need to make a cavity in the material. In a liquid dielectric, the body forms a cavity around itself in such a way that it displaces the liquid from the volume it is to occupy. The field strength EC inside the cavity will be different from the field strength in the dielectric medium. Hence, the force acting on the charged body in the cavity cannot be equal to the product of the charge Q and the field strength E in the dielectric. If we want to calculate the force acting on a charged body in a liquid dielectric, we must also take into account the fact that a mechanical pressure acts on the dielectric at the boundary of the body, which corresponds to a mechanical force Fm exerted on the body. As a result, the force acting on the charged body in the dielectric cannot be determined by the equation seen above, and its calculation is usually very complicated. In the case of liquid dielectrics, however, these calculations provided a very interesting result, according to which the resultant force F of electrostatic and mechanical forces is equal to the product of the charge Q and the electric field strength E. In the next step we introduce electrostatic force density representing the electrostatic force exerted per unit volume on a medium by an electric field, which is measured in Newton per cubic meter. This figure showing the force vectors over the boundary surface of a dielectric in an electrostatic field E illustrates how the electrostatic force density F describes the spatial distribution of electrostatic forces across a continuous volume. We can express the electrostatic force per unit volume from the equation stating that the force acting on a small charged body is equal to the charge Q of the body times the electric field strength E at the position of the body. As a result, the electrostatic force density F at a given point is equal to the free charge density ρ times the external electric field strength E acting on the charges, where both quantities are evaluated at that point. The total electrostatic force F acting on a charged body is given by the volume integral of the electrostatic force density F over the volume V of the body. By substituting the expression obtained for the force density into this integral, the force F can be written as the volume integral of the volume density ρ of the free charges times the external electric field strength E. As already stated, the total force given by the volume integral of the force density has a more complicated form in the general case due to mechanical forces such as structural stresses and pressure gradients. Now we will study the electrostatic forces present in a charged parallel plate capacitor with a dielectric medium between its plates in two different experiments. In the first one we consider two charged parallel plates immersed in a homogeneous liquid dielectric. We assume that the distance between the plates is very small compared with the dimensions of the plates, that is the electric field due to the charges on the plate is uniform between the plates and effectively zero outside the plates. Hence, the dielectric fluid will be polarized only within the spatial volume between the plates. Due to the polarization, opposite bound charges with the uniform surface charge density sigma prime appear on the boundary of the liquid adjacent to the internal surface of the plates. As a result, the electric field change within the dielectric medium and the net electric field has no effect on the charged plates. In other words, the polarization of the dielectric does not modify the force exerted by the plates on each other, that is the force of interaction between the plates is supposed to be the same in a vacuum and in a liquid dielectric. In reality, however, this is not the case. Experiments show that the force acting between the plates immersed in a liquid dielectric of relative permittivity epsilon r is epsilon r times less than the force exerted in a vacuum. We have the same findings in the experiments conducted with dielectric media in gaseous state. In the case of solid dielectric materials, such experiments are difficult to perform in practice. The change in the force acting between the plates cannot be explained by the presence of the bound charges, but it is due to mechanical stresses produced in the dielectric media. The result of such experiments can also be interpreted as follows. For the same amount but opposite charges on the plates, the energy U of the electrostatic field produced by the charges is given by 1/2 times the square of the amount Q of charges on each plate, over the capacitance C of the plates immersed in the dielectric fluid. We already saw that the capacitance C of a parallel plate capacitor with a dielectric material of relative permittivity epsilon r between its plates, is epsilon r times greater than the capacitance C0 of the same capacitor in a vacuum. If we substitute this expression into the right-hand side of the equation describing the energy U of the electrostatic field between the charged plates immersed in the liquid dielectric, we find that it is epsilon r times less than the energy U0 of the charged plates in a vacuum. Now we apply the principle of virtual work, where the distance x between the plates is changed by an infinitesimal amount. The principle states that the infinitesimal virtual work W done by the electrostatic force moving one of the plates is the product of the force Fx and the infinitesimal distance x covered by the moving plate. Since the virtual work done by the electric field reduces the energy of the field with the equivalent amount of energy, we can formally divide the virtual work or the negative change in the energy U by the infinitesimal distance. Then we can write the force F acting in the x direction perpendicular to the plates as the negative partial derivative of the energy U of the field with respect to the distance x. By substituting the expression for the energy U of the electric field into this equation, we obtain the equation stating that the force F acting in the x direction between the plates is epsilon r times less than the force F not acting in the x direction between them in a vacuum. This explanation only holds for liquid dielectrics. Any infinitesimal motion of conducting materials surrounded by solid dielectrics can modify the state of the insulating medium related to the mechanical stresses, and hence its electric properties. In such a case we even need to take into account the change in the mechanical energy stored in the materials in the system of conductors and dielectrics. In the second experiment, we insert a dielectric slab of relative permittivity epsilon R into the space between the plates of a charged parallel plate capacitor, where the dimensions of the plates are given by the lengths Lx and Ly, and d denotes the distance between the plates. If the space between the plates is completely filled with a dielectric medium, then the capacitance of the capacitor will be epsilon R times greater than its capacitance in a vacuum. Let us consider the situation where the dielectric slab is not fully inserted into the space between the two charged plates, and its position is described by the distance x measured along the motion of the slab. As a result, there is a free volume between the plates with a vacuum or air beside a volume occupied by some part of the dielectric slab. In such a situation, a force F is exerted on the dielectric pointing inward the capacitor, which is related to the non-uniform electric field at the edge of the plates of the capacitor, and its quantitative analysis is complicated. If we do not want to examine this effect in great detail, then we can calculate the force F by applying the law of conservation of energy in a similar way as it was derived from the principle of virtual work in the first experiment. We already saw that the energy U of the electric field of a charged capacitor is equal to 1/2 times the capacitance C of the capacitor times the square of the voltage V between its plates. The law of conservation of energy states that the change in the energy of the capacitor is equal to the work done on the slab by the electrostatic force F in the x direction. Then this force can be written as the negative partial derivative of the energy U of the electric field with respect to the distance x along which the work is done by the electrostatic field. If we substitute the expression describing the energy U into the right-hand side of this equation, then we obtain negative 1/2 times the square of the voltage V times the derivative of the capacitance C with respect to x. As the formula shows, we need to know the explicit dependence of the capacitance of the capacitor on the distance x describing the position of the dielectric slab between its plates. By examining the geometry of this setup, we can see that it is equivalent to two charged capacitors in parallel connection, where the first one has a vacuum or air between its plates and the second one has the dielectric medium of relative permittivity epsilon R between its plates. The capacitance C1 of the first capacitor is equal to the vacuum permittivity epsilon naught times the ratio of the area A1 of its plates over the distance d between its plates. Similarly, the capacitance C2 of the second capacitor is given by the vacuum permittivity epsilon naught times the relative permittivity epsilon R, times the ratio of the area A2 of its plates over the distance d between its plates. As the figure shows, the area A1 over the plate of the capacitor is equal to the difference between the length Lx and the distance x times the length Ly, whereas the area A2 is simply equal to x times Ly. We already proved that the total capacitance of capacitors connected in parallel is given by the sum of the individual capacitances, that is, the capacitance C of the capacitor in the experiment is equal to the sum of the capacitances C1 and C2 of the capacitors in the equivalent circuit. If we substitute the expressions for the capacitances into the right-hand side of the equation, where the areas can be expressed by the linear dimensions Lx, Ly, and x, then the capacitance C can be written as the vacuum permittivity epsilon naught times the ratio of the length Ly of the plates to the distance b between them, times the quantity of the length Lx minus the distance x plus the relative permittivity epsilon R times the distance x. If we substitute this expression into the force equation and calculate the derivative, then the force Fx acting on the dielectric slab can be written as negative 1/2 times the square of the voltage V through the capacitor, times the ratio of the vacuum permittivity epsilon naught times the length Ly of the plates in the direction perpendicular to the motion of the slab to the distance d between the plates, times the relative permittivity epsilon R of the dielectric minus 1. We note that the force acting on the polarized dielectric slab is proportional to the square of the potential difference between the plates, where the constant of proportionality depends on the geometry of the capacitor and the relative permittivity of the dielectric material. We can also interpret other well-known phenomena in electrostatics based on the polarization of dielectrics. When a charged object attracts small bodies made of insulating material, for example when a piece of amber rubbed by wool or a glass rod rubbed by leather attracts small bits of paper, we can talk about an effect caused by polarization charges. A glass rod with positive electric charge will attract the negative polarization charges on the bits of paper and repel the positive polarization charges on it. The net force will be attractive since the field strength closer to the rod is greater than the field strength farther away. The very nature of the mechanism of attraction is the spatial non-uniformity of the electrostatic field around the charged body. The attractive force always points from the place where the field strength is smaller to the place where the field strength is greater. If the electrically neutral bodies made of dielectric material are small, like the bits of paper, then the polarized dielectrics can be approximated as electric dipoles, and the electrostatic force attracting them is relatively easy to determine. By considering the polarized small bodies as induced dipoles, we can describe them with the electric dipole moment P given by the polarization charge q times the distance vector d pointing from the negative charge to the positive one at the two ends of the dipole. In the case of a point charge q, the force F acting on the charge in an electric field is equal to the amount of charge q times the electric field strength E evaluated at the position of the point charge. In the case of the electric dipole, the net force F acting on the dipole is the vector sum of the forces acting on the charges at the opposite ends of the dipole. Thus F is given by the charge q times the electric field strength E evaluated at the position vector or pointing from an arbitrary reference point O to the midpoint of the dipole, plus 1/2 times the distance vector d, plus the charge q times the electric field strength E evaluated at the position vector or minus 1/2 times the distance vector d. If we factor out the charge q, then we only need to determine the vector sum of the field strength evaluated at the opposite ends of the dipole. For a small polarized dielectric, the distance d is also small, and we can expand the electric field strength about the opposite ends of the dipole at the distance of 1/2 times d from its midpoint. Then the field strength E evaluated at r plus 1/2 times d has the Taylor expansion of the zeroth order term E evaluated at the midpoint r, plus the first order term 1/2 times the directional derivative of E in the direction of the vector d, plus the higher order terms. Similarly, we can expand the field strength E evaluated at r minus 1/2 times d as E evaluated at the midpoint r, minus 1/2 times the directional derivative of E in the direction of d, plus the higher order terms. Here 1/2 is factored out from the directional derivative, which is a linear operator. Hence, the electrostatic force F acting on the dipole can be approximated by the charge q times the vector sum of 1/2 times the directional derivative of the field strength E in the direction of the vector d with itself. This sum gives the directional derivative of the field strength E in the direction of the charge q times the vector d. Since q times d is the dipole moment P, we can express the force F exerted on the induced dipole by the electrostatic field E as the directional derivative of the field strength E in the direction of the dipole moment P of the dipole. We already saw that the dipole moment P of a molecule is equal to the molecular polarizability alpha of the molecule, times the field strength E of the local electric field polarizing the molecule. In fact, this relationship can also be applied for a single induced dipole representing a small polarized body, where we can write the dipole moment in terms of the external field E applied on the body if we replace the polarizability alpha with the effective polarizability alpha E including the local field correction. Then the force F is given by alpha E times the directional derivative of the field strength E in its own direction. Now we transform the derivative by using the vector identity for the gradient of the dot product of two vectors, let us say v and w, stating that the gradient of their dot product is equal to the derivative of w in the direction of v, plus the derivative of v in the direction of w, plus the cross product of v with the curl of w, plus the cross product of w with the curl of v. For v and w equal E, this identity can be reduced to the equation stating that the gradient of E squared is given by 2 times the derivative of E in the direction of E, plus 2 times the cross product of E and the curl of E. The second term in the right-hand side vanishes due to the fact that the electrostatic field E is curl-free. If we substitute this result into the force equation, then we conclude that the force F acting on a small dielectric body polarized in an electrostatic field E is equal to 1/2 times the effective polarizability alpha E of the dielectric, times the gradient of the square of the magnitude of the field strength E. Unlike the previous example with the parallel plate capacitor, we have proven that the electrostatic force acting on a small polarized body is proportional to the gradient of the square of the electric field strength, instead of the square of the potential difference measured in the direction of the gradient of the field. At the same time, it can still be shown that the effective polarizability representing the constant of proportionality can also be expressed in terms of the permittivity of the given dielectric, and it depends on the shape and size of the body.